Now over here, I'm going to draw out a table for us, and we're going to fill in this table together to summarize everything that we've gone over in this procedure of glycolysis and the Krebs cycle and oxidative phosphorylation, including the electron transport chain, together so far. So we are going to go over 5 key topics in this table that we're going to fill in together. The first is going to be the source, which basically refers to which stage in the process we are referring to within cellular respiration. The next is going to be carbon flow. So remembering that energy and matter can neither be created nor destroyed, right? It must always be accounted for in a closed system. So since this is a system where we are dealing with matter, we must always be able to account for the different components of this cycle. So specifically, we are keeping track of carbon. So we're going to look at carbon flow to make sure that the numbers balance out. If 6 carbons go into the system, that means 6 carbons have to be there at the end of this whole process, right? All matter must be accounted for. Next, we're going to go into substrate level phosphorylation. So keeping in mind that if we're talking about substrate level phosphorylation, we're talking about specifically the phosphorylation of ADP to ATP. So this is us looking into direct sources of ATP in cellular respiration. So where do we get energy without needing to use the electron transport chain, right? Where do we get ATP from the system without having to use oxidative phosphorylation? And then after that, we will look into oxidative phosphorylation, right? Here, this is where we will look at where we get, or how many ATPs we get from our electron carriers that have brought electrons to the electron transport chain for oxidative phosphorylation. So again, the phosphorylation of ADP to ATP, but this is the phase that requires oxygen as that electron acceptor. And so here, this is going to tell us how much ATP we get from that last stage of cellular respiration. And then this final column is where we will write out the ATP maximum yield. So this is where we'll do, our math will be in this column, and then we'll also have a little bit of math on the bottom where I'm going to actually put in the totals for everything. All right, so starting with glycolysis. In glycolysis, we started with glucose, which is a 6-carbon molecule. So we are starting with 6 carbons. And from glucose, through the litany of procedures that occur during glycolysis, we end up with 2 pyruvate molecules. And each pyruvate molecule is made up of 3 carbons. So far so good, right? 2 times 3 is 6. So all of our carbons in the system are still accounted for. We started with 6 carbons, and so far we still have 6 carbons total through 2 pyruvate molecules, each with 3 carbons. Next, we have what we sometimes call our transition reaction. And this is when we are converting pyruvate into acetyl-CoA right before the big part of that Krebs cycle starts, all right? So some people lump all this together, but a lot of times we like to really separate glycolysis and the citric acid cycle by saying that the conversion of pyruvate into those acetyl-CoA molecules is a transitional reaction occurring and bridging glycolysis to the citric acid cycle. So from our 2 pyruvate molecules, each that have 3 carbons, we get 2 acetyl-CoA molecules, right? Each pyruvate gets converted into an acetyl-CoA molecule, and each acetyl-CoA molecule has 2 carbons. And so now you're like, oh no, we don't have equivalent carbons, right? We went from 6 carbons from our 2 pyruvate molecules down to 4. So how can we account for all of our carbons? But wait, during this phase, we also released carbon dioxide, right? For every pyruvate molecule that is converted into acetyl-CoA, we lose 1 carbon dioxide. So for 2 pyruvate molecules, that would mean we're losing 2 carbon dioxide molecules. And there's 1 carbon molecule in every CO2 molecule, so 2 carbon dioxides would mean we're losing 2 carbon molecules, right? So we have 2 acetyl-CoAs, and each have 2 carbons. 2 times 2 is 4, plus 2 more is 6, so we're still on track. And next we have our citric acid cycle, right? The citric acid cycle. And in the citric acid cycle, where we have our acetyl-CoA undergoes chemical reactions that are followed by many, many more chemical reactions to complete the whole cycle. But long story short, throughout this entire cycle, we end up releasing 4 carbon dioxide molecules. And so from this, if we wanted to keep track of all of our carbon that is going into the system versus coming out, so now we're looking at the total, we started with 1 glucose molecule, which is made up of 6 carbon molecules. And through this process, we released 6 carbon dioxide molecules. And each carbon dioxide only has 1 carbon. And so the net total of carbons balances out, right? We put 6 carbons into the system and we left the system with all 6 carbons accounted for. They were just released as carbon dioxide. And through this process of basically breaking down glucose into smaller and smaller molecules, we produced ATP. And so let's go ahead and move on to the next column of our table, starting with glycolysis, looking at substrate level phosphorylation. Remembering that this is where we are looking at the direct production of ATP, where we do not need the electron transport chain, but just how much ATP are we producing in the system before oxidative phosphorylation. Sound good? So in glycolysis, we produce a net total of 2 ATP per 1 glucose molecule. Remembering that even though we produced 4 ATP in total, we had to spend 2 ATP to get those 4. So net total, we have 2 ATP from glycolysis. Then in the transition reaction, we produce NADH, right? But we don't actually produce any direct ATP. NADH is an electron carrier, and so it has to go through the electron transport chain or interact with the electron transport chain in order for ATP to be produced. So no ATP produced directly from the conversion of pyruvate to acetyl-CoA. However, in the TCA cycle, we do get GTP produced, and GTP does not need to go into the electron transport chain. It doesn't need to undergo oxidative phosphorylation in order for ATP to be produced. GTP can be actually directly converted into ATP. And so for each cycle of the TCA cycle, we get 1 GTP molecule. But remember, 1 glucose molecule produces 2 pyruvate molecules, which means now we are dealing with 2 rounds of the TCA cycle. So that would mean total for 1 glucose molecule, we would be getting 2 GTP, which is equivalent to 2 ATP. So this would total up to 4 ATP molecules before oxidative phosphorylation even happens. Now, oxidative phosphorylation, though, as you're gonna see, this is where we get the maximum amount of energy. So starting with glycolysis. From glycolysis, we get 2 NADH molecules. And once those 2 NADH molecules undergo oxidative phosphorylation, we end up with 6 ATP. Remembering that for each NADH molecule is equivalent to about 3 ATP molecules once they've gone through oxidative phosphorylation. So we get 6 ATP from those 2 NADHs that we got from glycolysis. Now moving on to the transition reaction, we also produced 2 NADHs, remembering that we are accounting for 2 pyruvate molecules, right? So a single conversion of pyruvate to acetyl-CoA produces 1 NADH, but this happens twice for every 1 glucose molecule. So for 2 NADHs, we would get, again, 6 ATP from those 2 NADHs. Now here comes the busy part, the TCA cycle. This is where we get a lot of our electron carriers, right? This is where we get the bulk of our NADH as well as FADH. So we have, from the TCA cycle, 3 NADH molecules per cycle, but remembering 1 glucose molecule results in 2 cycles. So 3 times 2 is 6, right? So we get 6 NADH molecules. And remembering that NADH is equivalent to 3 ATP, so 3 times 6 would be 18 ATP molecules from 6 NADHs. And then for each cycle, we produce 1 FADH molecule. But again, we're dealing with 2 cycles, so we are now dealing with 2 FADH 2 molecules. And for every FADH, we get 2 ATP about. And so that would mean we get 4 ATP from our 2 FADH molecules. Make sense? So now adding all of this together, I'm going to go ahead and highlight our different ATP amounts. So on the substrate level, we got 2 from glycolysis and 6 from oxidative phosphorylation, totaling 8 molecules. If we have maximum yield, that is, right? We're talking about perfect system, right? So if this were a perfect system, we would get a total of 8 ATP molecules just from glycolysis if we include the ATP that comes about through oxidative phosphorylation at the very end of cellular respiration. And then for the transition reaction, we get 6 ATP total. From the TCA cycle, we get 2 plus 18 plus 4, which totals to 24. And so adding all of these together, if we want to go down the line first for our oxidative phosphorylation, sorry, I forgot to add all those up for you first. Oxidative phosphorylation altogether, we have 6 plus 18 plus 4. That would be 34 ATP just from oxidative phosphorylation. And then if we want the grand total maximum yield of ATP, we add all these together. They should add up, as well as adding these ones together. They should add up to the same number if we did everything right, and that would be 38 in a perfect system. Now remembering that in reality, we're going to end up somewhere with between 30 to 36 because it costs energy to transport things and make energy. Sound good? So if you've ever heard that cellular respiration produces exactly 34 ATP, that's probably because people are mistakenly only referring to the energy we get at the very end through oxidative phosphorylation in a perfect system. They're basically excluding the ATP we produce directly in this whole process. They're only looking at a part of the whole. But the total maximum yield in a perfect system would be 38 ATP, which in reality will equivalent to about 30 to 36 ATP. Well, hopefully this discussion was really helpful to you, and I hope that this helped provide clarity to certain aspects of cellular respiration. Thank you so much for going through all this with me. We started with glycolysis, which happens in the cytosol of the cell, went all the way through the Krebs cycle inside of that mitochondrial matrix, and then ended with oxidative phosphorylation, the electron transport chain, in our mitochondrial membrane. This helped clarify things for you, and I wish you the best of luck moving forward.